Hello, my name is Kishan Shenoi, and this presentation is on synchronization as it applies in mobile and telecom networks. It is a module of the WSTS tutorial session which is being made available online ahead of the workshop, I guess just to get people up to speed on it and give them a flavor of what is coming. As we've indicated in earlier presentations, timing alignment is fundamental in telecom. Wireless networks, for example, the digital transmission, fundamental transmission, involves some notion of synchronization because the receiver has to do carrier recovery. In wireless cellular, there's some additional requirements regarding timing, and in particular aligning base station clocks, because you need this alignment in order to provide certain services. There are two other aspects which at first I was thinking of adding, namely circuit switched or TDM networks, and talk about synchronous time division multiplexing, and packet switch networks like circuit emulation, which those, however, are, I believe, of less importance at this stage. So if there is some questions, I can answer them. In early wireless networks, the synchronization requirements were primarily couched in terms of frequency accuracy, and this would be the frequency of the carrier. Now, this carrier would be in the 800 megahertz to a few gigahertz range. Now it's getting to be a little higher as well. But the requirement was just on the accuracy of the frequency. As we went on with CDMA IS-95, that was the first scheme to introduce the need for phase or time accuracy. And this is because base stations would basically transmit on the same carrier frequency and use the same PN code for spreading, but would distinguish each other by time. So essentially by code phase. Now with LTE, for example, LTE TDD, both the uplink and downlink use the same carrier frequency or the same channel. So they separate each other in time in the up and downstream directions. New technologies like comp, carrier aggregations, geolocation, and other services and functions with a lot of acronyms, they all deal with signal processing and consequently are necessarily synchronized properly. In fact, the degradation with lack of synchronization is dramatic. So why do we need a good frequency? This was a fundamental thing in wireless, where the user equipment, the actual mobile phone, could be in motion, like you're in a car on the autobahn and traveling at several hundred kilometers an hour. As you're moving, that introduces a Doppler shift, and so when you hand off from one base station to another, the mobile has to reacquire the carrier frequency, and if there's a large frequency offset between the base stations that it's handing off, moving to, that makes it difficult to reacquire, and consequently you could have call drops where it just can't hand over properly. In CDMA or IS-95, the base stations were distinguished by their time offset, and that implied that base stations had to maintain a time alignment error. Now this is in time of less than 10 microseconds. In modern wireless, LTE and 5G, you have TDD, for example, time division duplex, that requires a time alignment error of less than 3 microseconds. And for some services, like in 5G clusters, which I will talk about later, a time alignment error has to be less than 130 nanoseconds. Like I said, I'll talk about one of the applications, like coordinated multipoint. What is this? This is a situation where one UE, one mobile, can communicate simultaneously with more than one base station. Consider two base stations, for example, and you can get simultaneous data transmission from multiple sites, multiple base stations to a single UE. Or you can have the single UE talking simultaneously to two base stations. So you have the joint transmission and joint reception. And performance, clearly we are doing this to improve bandwidth or improve the information transmission rate. The performance is a function of time alignment error. The larger the time alignment error, the more difficult it is to get this aggregation of bandwidth. As we had said earlier in an earlier presentation, signal processing is involved, and that requires synchronization. And according to 3GPP, the typical time offset at the UE, in order to support joint transmission, should be less than 2 microseconds, as measured at the UE. For joint reception, the requirements are still being worked out. The place where timing is really involved is not in the core of the network, which is basically all packets, and it can be asynchronous. It's in the radio access network, and we'll talk. So our focus is going to be on the RAN. The RAN architecture has seen quite a bit of evolution. If you think of the traditional RAN equipment, the base station was integrated. The baseband processing, which is the modulation and the compression, etc., and the RF processing was all done in one unit, and there was one backhaul back to the mobile core. Then we went to the notion of a centralized RAN, where the baseband unit, which had the compression, decompression of the voice and data, that would be done in a BBU, which would be in a pool, like in a BBU hotel. And each unit there would connect to an antenna unit, or RRU, over fiber using a scheme called CPRI, which comprised the front haul network. There would be a link back from the BBU pool to the mobile packet core. Then we get into this notion of the open RAN for 5G, where the BBU is further split up into the DU, or distribution unit, which would handle the compression, decompression, and the CU, which would handle some higher level protocol aspects of the processing. And from the DU to the RU would be a separate network called a front haul, which could be packetized as well. The backhaul back to the mobile packet core would be from the CU. The ORAN Alliance has been looking at 5G and looking at all the various functions involved and seeing how to split them apart and define open interfaces for them. It looks like the split, for example, between the DU and the RU, the basis is a compromise between the data transfer requirements of the front haul and the processing complexity of the RU. What has been kind of agreed upon so far, it appears, is what the so-called 7-2 split, which is shown in the right-hand side of the slide. And basically, the DU does a lot of the baseband processing, and the RU does just the conversion from digital to analog, and the various beamforming, and the IFFT and CP have something to do with the actual modulation schemes required. ORAN has taken synchronization very seriously. In fact, they refer to that as the S-plane, the synchronization plane. You have the data plane, the control plane, and the S-plane. It's been elevated. It's not just an afterthought anymore. In 5G, and this is, I'm going to talk about this in the context of ORAN, but it applies in any case. When you can think of base stations or antennas which are closely related to each other geographically, you can think of them as in a cluster, and then you can start working back to the core network. So the time alignment error within a cluster, we would expect that to be less than 130 nanoseconds. Now, there are two base stations which are far apart and they're not really in a cluster, then you have a different time alignment requirement, and that is the traditional 3 microseconds. Now, when you think about this 3 microsecond time alignment error, if the antenna units can be traceable to a single source or common source, the time error between the antenna and that common source should be less than 1.5 microseconds. When you start thinking about it in clusters, the source for the whole cluster may be not necessarily in the core, but much closer to the antenna units. And in that case, the time offset between the antenna unit and the source closer to it needs to be of the order of 65 nanoseconds. For the purposes of beamforming between any two RF units, between any two antennas in a MIMO, for example, you need a lot more stringent requirements for time alignment error, and that comes down to often in the 10 nanosecond range, and it's usually not done by distribution, it's done by calibrated coax cables. It's in an analog manner. This tight synchronization can be simplified by moving the source, for example the PRTC or GM, as close to the endpoint as possible. The ORAN, the so-called S-plane, they refer to the LLS as the low-level split. They have 4 different configurations, C1, C2, C3, and C4. I just talk about one, C2, and the others are in backup slides. So in configuration C2, we imagine there's a front haul network between the DU and the RU, and the DU is where it acts essentially like a local grandmaster for the RU units which are subtending from it, and the front haul network is full on-path support. And so you can think there on the left there are two pictures shown, just each with a slightly different twist to it. But the one on the right shows the typical sync flow, which goes from the local GM to the DU itself through fronthaul switches to the radio unit. The typical telecom profile uses the telecom profile 8275.1, which is a layer 2 full on-path support with sync E. Though sometimes it may be difficult to ensure that all the switches in the front haul are capable of sync E and full on-path support. So in those cases, an 8275.2 profile needs to be used, which will require a more efficient servo in the slave unit of the RU. The next 2 slides are tables, which show some of the specifications provided by 3GPP. I won't go through all of them. I won't go through any of them. You can just look at them. The source is 8271, and that gives the time and phase end application requirements and points to other sources where the specification is detailed. This is the second. Well, that brings me to the end of this module, at least as far as the presentation goes. Thank you very much for listening. If you have any questions, comments, suggestions, please don't hesitate to contact me. I have my email given there. In the deck, I have included several other slides to cover items other than just the wireless aspect of synchronization. So peruse them, and if you have any questions, please don't hesitate to ask. And hopefully you can catch me on the floor of WSTS if you have any other questions. Thank you.